Okay, let's unpack this. I have a confession to make. This morning, I was trying to make espresso.
Oh, no.
Yeah, and I packed the coffee grounds way, way too tight.
Rookie mistake.
I know, I know. I just stood there staring helplessly as the machine strained, and not a single drop of coffee came out.
Completely blocked.
Totally blocked. Frustrating, yes. But as I was reviewing today's sources for our deep dive, I realized my morning caffeine failure is actually the perfect, tangible example of percolation theory in action.
It really is a perfect analogy.
Right. Now, I know you, the listener, are likely familiar with the basics of network theory, so we aren't going to spend time defining what a node is. The mission of our deep dive today is exploring this math of random networks. Basically, if you pour liquid on top of a porous material, will it find a path of connected holes to reach the bottom?
And what's fascinating here is how practical the origins of that question are. You'd assume this highly abstract mathematical field started in some, pristine computer lab.
Right, like standard theoretical physics.
Exactly. But it actually began in the 1940s with the coal industry, specifically with the legendary chemist Rosalind Franklin.
The Rosalind Franklin, I love that detail in the research.
Yeah. She was studying the density and porosity of coal to optimize filters for gas masks.
So her work on physical sieves directly inspired the math.
It did. By 1957, statisticians Simon Broadbent and John Hammersley took that inspiration to mathematically model how fluids move through a random maze of open or closed tunnels.
Okay, but I want to make sure I'm grasping the two core models they establish. Is it fair to say bond percolation is like modeling road closures, while site percolation is like modeling whether the cities themselves are shut down?
That's a really decent starting point, yeah. But to be precise, it's not just about what is shut down. It's about modeling the probability of continuous path existing from one edge of the system to the other.
Got it.
So, in your espresso pack,
My tragic espresso.
your tragic espresso. Bond percolation asks if the tiny channels between the coffee grains are open enough for water to pass. Site percolation asks if the grains themselves are porous enough to let water through.
Ah, okay, that makes a lot more sense. Finding the most efficient path through a complex, interconnected system is basically the holy grail, whether you're mapping physics or trying to scale a modern business,
Oh, absolutely.
which actually ties perfectly into today's sponsor. Building strong, connected networks is crucial, and that's exactly what Silk does. If you need help with AI training, automation, integration, or software development, they are the experts. Uncovering where agents could make the most impact for your business or personal life, check out embersilk.com for your AI needs.
Navigating those complex networks is no joke.
It really isn't. So jumping back into the math, here's where it gets really interesting to me. The sources highlight that when you add connections to a network, the connectivity doesn't just scale linearly.
Exactly. And this is the most crucial concept in percolation theory, the critical threshold.
The aha moment.
Yes, the phase transition. It doesn't just gradually connect. As you randomly add open links to a network, the probability of a fluid or an idea or a signal making it all the way across stays stubbornly close to zero.
So you just have these isolated islands of connectivity.
Just islands. Until you hit a specific mathematical fraction, the moment you hit that critical threshold, those tiny clusters instantly and sharply merge into one giant spanning cluster. For a 2D square lattice, that magical tipping point is mathematically proven to be exactly 50%.
It's literally like flipping a switch.
Exactly like flipping a switch.
So what does this all mean for us today? Because I saw hepatitis B heavily featured in the virology papers we reviewed. How exactly are biophysicists applying a 1950s mathematical network theory to biological viruses?
This is where the science gets incredibly optimistic. A virus like hepatitis B has a protein shell called a capsid.
Which is essentially a complex geometric lattice.
Precisely. Scientists are applying site percolation to this lattice. Because they understand the math of the critical threshold, they aren't just blindly attacking the virus. They are calculating the precise fragmentation threshold of that specific shell.
So they are basically treating the viral shell like a microscopic game of molecular Jenga.
That is a perfect analogy. By knowing the critical threshold, they can determine the exact fraction of structural proteins they need to remove or destabilize. They don't have to destroy the whole virus.
They just have to mathematically push the structure below its percolation threshold.
Exactly. And the entire viral shell completely collapses on its own.
That is a massive leap forward. Just mathematically targeting the right structural threshold is paving the way for such incredibly optimistic and advanced medical treatments.
It really is an inspiring application of abstract math. And if we connect this to the bigger picture, it raises a really provocative thought for you to ponder today. Think about the networks in your own life,
Like your social circles or your skills?
or even your creative ideas. What if you aren't failing to make progress, but are simply hovering right below that critical threshold?
Just one or two connections away from a sudden, massive breakthrough.
Exactly.
What a brilliant way to look at it. If you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.